Welcome to our discussion on the evidence for electron structure. Today we'll be talking about two sources of evidence that have convinced us that electrons are organized in the electron cloud into energy levels and sublevels. Our first piece of evidence will be emission spectrums, and then we'll look at photoelectron spectroscopy. Let's get started. So our first thing is emission spectra. And when we find that when we send an electric current through a gas, that gas starts to glow and give off light. And for each gas that we send electricity through, it gives off a distinct color. For hydrogen, for example, is this weird like pinky purpley color that it gives off. Now hydrogen could produce that pinky purple color in a couple different ways. First of all, it could give off just one wavelength of light exactly at that pinky purple color. The other option is that it can actually be given off multiple different colors of light that mix together to make that pinky purple. So maybe it's like some red with some blue to give it a little purple, then some orange to make it kind of pinky colored, or there's just multiple ways of doing it. To know what's really happening, we have to use what's called a spectrometer, which is basically a little device with a prism that breaks light into its component color. When you look at a spectrometer, you may have used them already. They're like typically little black pieces of plastic, and you look inside them and point at the light and you see all the bands of color. It lets you know what color of light is made of. When we do this with hydrogen, we find that pinky purple color really isn't just one wavelength, it's composed of a couple wavelengths. So there's this red band of light, this teal, blue, and a couple purples, and those five added together give you that pinky bluey, purpley color that hydrogen makes. Now this was very confusing to folks, and this is actually called the emission spectrum for hydrogen here. This was very confusing for people because there was no reason to believe, or there's no reason to understand why hydrogen would give off these specific lines and not just a full spectrum of color. Until Bohr proposed a hypothesis that maybe the electrons in hydrogen weren't actually free to go anywhere, but they were organized into energy levels. So that hydrogen, so an electron could transition from the first to the second and back, but not halfway in between them. And that would explain these bands of light would be then the transitions. These are the jumps that are possible. So there's no jumps that correspond to this energy anywhere in the atom, but there's another jump here that corresponds to this energy. And that's proved to be a correct hypothesis. So when an electron absorbs energy from some source, it jumps out of its normal energy level, which is called the ground state. It's the lowest energy level it can get to. And when it absorbs energy, it jumps up to a higher energy level. And we call that the excited state. So it goes from its ground state up to excited state. That's absorbing energy. Now that electron won't stay there. It's going to fall back down to its ground state. And when it does fall back to its ground state, it's going to give off a little burst of energy called a photon. So it's a little burst of light, and that energy of that photon, that light, is going to be related to how far down it jumped. If the electron makes a big jump, it lost a lot of energy. That photon then has a lot of energy. If it makes a tiny little jump, the electron didn't lose much energy, so a photon has very little energy. Okay? So that's basically how the electrons are working, and that's what gives these bands, these hydrogen emission spectrum. Now, before we move on, we got to talk a little bit about the color of light. So the color of light is related to its energy, frequency, and wavelength. And you may have remembered this little mnemonic device, Roy G. Biv. It's like somebody's name. It lists the colors of the spectrum of the rainbow in order from lowest energy to highest energy. So over here we say this is the low energy spectrum. This is so low E, this is high energy, and it goes from here to here. Woo. Now you know that a low energy wave is going to have a long wavelength, and a high energy wave is going to have a really short wavelength. Right? So we have long waves, short wave. These are long waves. These are short waves. And then also, to make this wave, if you were going to make this on a slinky or on like a rope, you would move your hand slowly. And that would correspond to a low frequency light. And this would be obviously a high frequency light. So high energy, high frequency, short waves. Low energy over by red, low energy, long wavelengths, low frequency. So violet lights are higher in energy than red and across. Now here's a nice little graphic that shows this as well. Now visible light is just the light that our eyes have evolved to see. It is only one tiny part of the spectrum. And this was drawn really well to scale. This would actually be a much smaller sliver. And so lower in energy than visible light, what we've evolved to see, is a light called infrared light. Our eyes can't see it, but it is still there. We can build devices to see it. So night vision goggles use infrared light. There's also microwaves with even lower energy, and then even radio waves. So we can send information and energy through waves. And then above visible light is a region called ultraviolet. And this light we cannot see, but this does ultraviolet light does damage to our skin. It gives you sunburns and can cause skin cancer. And then, of course, X-rays are even higher energy light. We use them to actually image bones inside of your body. And gamma rays can be used to treat some types of cancers. And there's one more you may want to know that's really high energy, and it's called cosmic rays. So cosmic rays are even higher energy than gamma. They're over here. And again, short wavelengths are high energy. Long wavelengths are low energy. All right. Now these photons of light give us direct evidence of energy levels in the atom. Remember, here's our hydrogen again. Here's our hydrogen spectrum again, and we have these 5 bands. Let's see what's going on when we do this. So here's our hydrogen atom. Here's the nucleus. So there's a proton down here in the nucleus here. This is the first energy level, the second, the third, the fourth, the fifth, and the 6th. Now notice something about the energy level spacing. The first energy level is super close to the nucleus and is a really low energy state, so it's really tightly held to the nucleus. The second energy level is really far away, and the difference between the first and second energy level is a big difference in energy. The difference between the second and third is smaller, fourth and fifth and sixth. They keep getting smaller differences between them. And that's going to continue on, and technically this has an infinite number of energy levels, but as you get really far up there in high numbers, the difference in their energies are really small and hard to distinguish between them. So the question is, where do these 5 bands come from? So let's look at the simplest transition. So an electron here, we have 1 proton, 1 electron. Our electron here might get excited and get jumped out to the second energy level. And once it does that, it will then fall back to the first energy level. And when it does that, it's going to give off a photon of light. Now, as we find out, that photon of light is a UV photon. Energy is too high for us to be able to see with our eyes. We don't see this transition. The next simplest one is going from the second energy level, so it got excited more now, it gained more energy, went all the way out to the second and then fell back down into the first. Now, if it does that, it gives off an even higher energy UV. Notice how this transition is bigger? There's a bigger difference in energy here, so it's higher energy light. And the third energy is even higher energy UV, and fourth and fifth and sixth. All of these are all UV light. We can't see any of them. All right, so that doesn't explain these 5 bands up here yet, because these are too high energy. They're way over here somewhere off the visible spectrum, so they're over here in the UV range. So what's the next simplest? So if an electron gets ejected or excited out to the second energy level, it can go back to the first, but it can do something else weird. It can actually go from the to the third energy level. It can go from the third energy level to the second, and then from the second to the first. It can make 2 jumps, giving off 2 different photons. This is that first jump. So it gets excited out to the third, jumps back down to the second. When it does so, it gives off this red band. This is the energy corresponding to this jump. Now, if it jumps from the fourth energy level to the second, that gives off this band of light. And jumping from the fifth to the second gives off the blue, sixth is the purple, and then the seventh, actually it wasn't drawn, but the seventh would be the next purple. Now here's some really cool stuff, check it out. This energy level is a big difference. The difference between here is still pretty significant between the red and the green, and there's a big band jump between here. But then here, this difference is smaller, and this difference is smaller. The difference gets smaller, and the spacing gets smaller as well. So that's kind of cool. That's evidence that these energy levels are spaced differently, right? So this is the burst of energy there. So this is the visible spectrum. So any transition to hydrogen from a higher energy level down to the second energy level gives us these bands. There's another one too. So what if you go from 4 to 3? And then 5 to 3. And notice that these jumps are smaller than even red. These jumps are on this side, and we call these infrared. So these are in the infrared region. We can't see them. These are in the visible region. It just happens that our eyes have evolved to see in this range of the spectrum. Right? All right. So that's the transitions for electrons and a hydrogen atom. Now in other atoms, it's just the same thing, but it's just more complicated because there's more electrons jumping up and down from different ground states, different excited states, so we just get lots and lots of different bands. But it's still the same process. Now there's another way of drawing this to make it a little easier to look at. Instead of drawing it as circle energy levels, we just draw the energy levels straight across. And you can see here that, bam, we have these UV, these big jumps from high energy down to 1. So these big jumps are all UV. This middle set of jumps are visible, and these smaller jumps are infrared. Now, if you're wondering why this one's so big, it's just because these aren't drawn to scale. They're spaced out. They should be much closer together and really small. This biggest infrared one should be smaller than the red. And in this case, it's not, but it should be. All right, so you'll see this kind of picture from time to time showing the transitions of electrons in atoms. And you should know that the small transitions are red, and the larger transitions are the violet colors. So there's that. Now, emission spectra are different from each element, like you said before, and you can see here calcium, argon, sodium, and krypton. They give off distinct energy or spectra. We can use that spectra to actually identify which elements are in a sample, and we call that process flame spectroscopy. Basically what you do is you put a sample into a machine, it heats the sample or drops it into a flame. When it does that, the electrons get excited, they give off all kinds of light, and depending on the bands of light given off tells you which elements there are. We can use this technique to figure out things like which elements are in a star, or which kinds of elements are in, say, a polluted groundwater or ground sample. You can find if there's chromium in there, molybdenum. You can find out if there's just nasty stuff in the sample, lead, those kind of things, using this process of looking at what bands they give off. All right, so that's our first evidence that there are energy levels in the atom. But what's the evidence that there are sublevels, this SPDF thing? So now we have to talk a little about photoelectron spectroscopy to understand that. Photoelectron spectroscopy basically is just a way of knocking electrons off of an atom and measuring the energy of those electrons to figure out where the electrons were in the atom. This device that you're looking at here in this picture is a photoelectron spectrometer. So it's a super cool thing. Basically what it is, I'll run you through the parts. Right through here is where you load the sample. So there's a long tube that goes in through here, and you slide your sample through this tube all the way down into the reaction chamber, which is back in here somewhere. It's like right, whoops. It's like right in here somewhere. Once you get your sample in there, you completely evacuate this. So you pump out all the extra gases, so nothing else is in there but your sample. You basically get it just like space. And to do that, there's a first stage pump here that pumps air out, and then this looks like their second stage pump that takes out the last bit of air, makes it like space on the inside here. Now this big device here is an X-ray generator. So you've got your sample in here, and you fire a beam of X-rays, so super high energy light at the sample. So your X-rays come in this way. When those X-rays hit electrons, they excite the electron so much, it actually just flings it completely out of the atom. So our samples right here, it gets hit. Those electrons come flying out of the atom this way. So these are electrons coming off the atom. Now, the amount of energy in that electron depends on two things. The energy it got from the X-rays, which you use X-ray source with a very narrow frequency of energy. So basically all the X-rays have exactly the same energy. So every electron absorbs the same amount of energy at the beginning. The electrons, though, that were held on the outside of the atom and not held very tightly, jump out of the atom, and they jump out with a lot of excess energy left over. So they jump out really fast. And as they jump out, the electrons travel through this dome shape here. There's this strong magnetic field. So let's say, I don't know, north is this way, south. And there's a strong magnetic field going through here. And as these electrons pass through this magnetic field, they're bent onto a detector on this side. They land right here. And this detector counts them, not only how many there are, but where they landed. Now, if you're on the outside of the atom, very little energy of the X-ray was used to jump you off the atom. So you jumped out going really, really fast and you spun around. And in here, you took a really wide path through this device and you landed on the far side of the detector. Now, if you're an electron that's held down in the lowest energy level, really tightly to the atom, coming off the atom, the entire time you're moving away from the atom, once you absorb that photon, that X-ray photon, you're slowing down because you're attracted to it. So you're still going to get away, but you're going to get away at a much lower speed. So you're going to hit this magnetic field at a lower speed, and just because you're going slower, you're going to get bent way more, and you're going to land like right here. And the detector's going to say, oh, here's an electron right here that landed right here. Here's an electron that was held really tightly by the atom. And it can count how many electrons are in that situation. Okay? So that's a very high-level explanation, a little bit simplified for what's going on with this thing. But basically what it can do is it can count how many electrons are held tightly and how many electrons aren't held tightly all throughout the atom as we bombard it with these super high-energy X-rays. And what it gives off is a PES, so Photoelectron Spectroscopy graph, and it shows a spike for the number of electrons at different energy levels. And this was like one of those blow your mind moments, because this was some really direct evidence for the things that we've been talking about so far. So notice, first of all, that this is the relative number of electrons, and this is how much energy they had when they were, or how much energy it took to get them out of the atom, right? So it looks like there's 2 electrons here that took a bunch of energy to get out of the atom, a whole bunch of energy, 433 whatever units here. I think it's electron volts, but whatever units, it's a lot of energy. And then there were 2 electrons, 2 more electrons, but they took less energy to get out. And then there were 6 electrons that took even less energy. And then 2 electrons that took even less energy, 6 electrons that took less energy, and then 2 electrons that took less energy, and 1 electron that took less. So it had this weird pattern of 2, 2, 6, 2, 6, 1, and 2. And if you remember that S electrons, there's 2 S electrons, S electrons, S electrons, P electrons. 6 electrons fit into P electrons, P and S. It's these numbers that gave us evidence for and reason to believe that they're organized into sublevels where it's 2 and 6. Awesome. Now, but which energy levels are which? And that's where things get a little bit tricky. So high energy values indicate the electron was difficult to remove, which means it must have been close to the nucleus. So this super high energy means that this was hard to remove, and I should say hardest, right? Hardest to remove, which means it must have been closest to the nucleus. So it's going to be a little hard to reason through this because this high energy one isn't the energy of the electron, it's the energy required to get it out of the nucleus. So this must be the first energy level, S electrons, and there are 2 of them. This is the 1s2 electrons. Isn't that cool? Now the next one we get to in terms of high energy, this is the next hardest to rip off. right? So if you look at an atom and, here's the nucleus, and here's the first energy level, here's the second, here's the third, here's the fourth energy level. Well, ripping off the electrons out here are going to be relatively easy, take very little energy. That's these guys. Ripping off the next energy level, right? That's these guys, is going to be a little bit harder. It's going to take more energy. The third energy level is going to take, wow, these are going to be hard to get off, right? So this one is going to be, so is the second energy level, sorry, it's going to be hard to get off. And that first energy level is going to be super hard to get off. That's these. So that's a 1s2. Now the next hardest one to get off are these second energy level, so that's 2s2. And this one is 2p6. And we'll also notice that, check out the banding here, that there's a huge difference in energy between these electrons and then these guys. It goes from 433 to like 48 and 39. And then there's these little chunk of electrons that are kind of togetherish. They're really close together. And then another big break and another chunk of electrons that are close together. And then another break and another chunk of electrons that are close together. So they're in this region here where they're clustered around, and it's kind of cool to see they're clustered as 8 as well. I mean, these are all like, whoa, it all makes sense. And this is all from that machine, right? These are all measurements. They're not something that was made up. All right, awesome. So let's keep going. So these ones that are weakly held must be a higher energy level. So this must be 3s, and this must be 3p, and a 6 and a 2 here. And then we keep going and we're saying, all right, so this must be the 4s2, and this one, what's next? Well, we're looking at our periodic table and say, oh, it's 3d1. So the electron configuration, I can figure it out from this and say the highest energy ones are the lowest energy levels, and I can work my way up. So 1s must be here, then this must be second energy level, third energy level, fourth energy level with that little 3d1. So if I was going to write this electron configuration, I'd say it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. This was direct evidence, and this is, of course, sorry, scandium. If it's a neutral atom, this would be scandium. So this was direct evidence that we have this internal structure to the energy levels. Like here's the energy level, right? First energy level, second, third. So this is first. This big jump between them, that goes to the second. Second. This goes to the third, and this goes to the fourth. And remember in hydrogen with those energy levels, they were farther out, but they were less far each time. Notice how the energy jump here is huge at first. This is a smaller jump, so from the 30s and 40s down to the single digits, and then an even smaller jump with the fourth energy level. So you can see that spacing gets tighter as well as it goes up. So even more evidence of even that part of the model. Really cool stuff. That's photoelectron spectroscopy in a nutshell. So on this one, what I want you to do is go ahead and pause the video and see if you can't work out which electrons are in which sublevels, and then the identity of this atom. When you get ready, when you answer these two questions, hit play and we'll go through the answers for you real quick. All right, so these two electrons way out here are the ones that are the hardest to remove, and they're grouped. So this is the first energy level. These two are close to, these are the second energy level. Because they're easier to remove, so they must be in the second energy level. This is the energy it takes to remove them. So here, this must be 1s2. This must be 2s2. And this must be 2p4. When I look on the periodic table, if this atom is neutral, this is going to be oxygen. Right? And I could just do that as well by counting the number of electrons. They say, okay, so 2, 4, 8 electrons, that's going to give me an oxygen atom. And then the thing, this next question is tricky. It says, what if this atom had a -1 charge to start with? Well, gosh, it wouldn't be oxygen, because an oxygen with 8 electrons would be neutral. But what would be a -1 with 8 electrons? Well, that would be a nitrogen, because nitrogen has 7 protons And this has 8 electrons. This would be a nitrogen -1. Well, if it's a -2 charge, then this would be a carbon -2 atom. So depending on what the charge of the atom is what atom it is. If it's neutral, it would be oxygen, a -1 nitrogen, and -2 carbon. All right, awesome. Well, that's it for our discussion today. If you were able to get this, you got the photoelectron spectroscopy. It's a wonderful evidence of all this internal structure of the electron cloud.